Okay, this is our first of many lessons on the basic atomic structure and for Unit 1. So this lesson is on atomic structure and some simple trends in the periodic table. What we're going to start with first is just looking at the atom and how it is arranged, the basic particles in an atom, and discuss some of their characteristics. So basically a review of grade 9 and 10 science. Now, of course, we know from experiments from Bohr and Rutherford that the majority of the space in an atom is actually taken up not by the nucleus, but by the space in which the electrons inhabit. Some of the things we need to remember about electrons is that they're very small. They have a net negative charge. All right, and for our purposes, we're going to think of electrons as almost like tiny little planets whizzing around the nucleus, and the nucleus could be thought of sort of like a sun, so more like a planetary model right now. Within the nucleus, we have two particles. We have a proton and a neutron. We know that in terms of the proton, it's about 1,800 times larger than an electron. It's got a positive charge, which is equal but opposite to an electron. The neutron, pretty much the same size as the proton, slightly bigger, but nothing we need to really worry about at this point. And it is neutral. Now, when we take a look at these particles, it's really important to go through a couple of the basics. One of the things we really need to remember is that neutrons, protons do not move in chemical reactions. That would be nuclear reactions. We're not going to worry about that. So for chemical reactions, what you'll get is a rearrangement of a nucleus. Some nucleus will connect with others, things like that. But in terms of moving, it is not the nothing in the nucleus is moving. However, electrons can jump from one atom to another, so these guys do move. And that's going to be really important, especially when we start taking a look at basic chemical reactions and things like that. What we also need to talk a little bit about is discussing some of the information that we'll get on a periodic table. Let's take an element like oxygen. Whenever we see oxygen, the chemical symbol for oxygen in a periodic table, we'll notice two sets of information. We'll see a number 8 typically on the top left-hand side, and a number such as 15.99 typically on the bottom. Now these two numbers represent different components of the atom of an oxygen atom. So the number 8 corresponds with the atomic number. Now atomic number is has been defined as the number of protons. Whenever I denote a proton, I'm always going to put a P with a plus sign on it. Alright, that's a symbol for protons. It's also equal to the number of electrons of the atom. And what that means is that this atom has not exchanged any electrons. Whenever there's an exchange of electrons for an atom, we're dealing now with an ion, so we don't call it an atom at that point. So atomic number, which is your smallest of the numbers, and it's always a whole integer, is equal to the number of protons, also equal to the number of electrons. Now the number on the bottom is our atomic mass. Now it's also been called the relative atomic mass, and there's a reason for that. We're going to notice here that we have a decimal. Some of you might think, well, where does that come from? Well, we look at the atomic mass as equal to the number of protons and the number of neutrons. Now the fact that we have a decimal here has nothing to do with a neutron or proton being slightly different in size. What it does have to deal with is the fact that in nature we have different sizes of oxygen atoms, and we call these isotopes. might be a little counterintuitive. You would think that all atoms of an element are the same. That's sort of what Dalton came up with his theories. But the fact is that atoms of an element can differ in the number of neutrons. And this is important to note here. And that's really important. What you'll see is the majority of oxygen atoms actually have 8 neutrons in the nucleus, which would give you an atomic mass of 16. 8 plus 8, 8 protons, 8 neutrons gives you 16. However, there's a small percentage of oxygen atoms out there that actually have one less neutron. So they only have 7, giving an atomic mass of 15. When we collect oxygen atoms and average the atomic masses of all of them, it comes out to be 15.99 because what we're looking at is the average. And so that's why we see these little decimals here. And typically when we start to do calculations in chemistry, we'll round up or round down depending on the if it's 0.5 or below 0.5. 0.5 we round up, below 0.5 we round down. This has some implications, especially when we look at some really interesting chemistry dealing with radioactivity. Some of you have heard of carbon. We know typically view carbon as having 12 particles in the nucleus, 6 protons and 6 neutrons, but we do have what we call carbon-14. Again, it only has 6 protons in the nucleus, but it will have carbon-14 has 8 neutrons. What's interesting about carbon-14 is that it's radioactive. You might have heard of carbon-14 dating. We use that to date fossils, date any type of organic matter. We all, as organic beings, are giving off a little bit of radiation. And what's happening is some of these, the 2 extra neutrons in carbon-14 actually decay. They break down and emit energy and particles. Now, it's not dangerous. Otherwise, we wouldn't be able to live. But some isotopes are radioactive, and when they're radioactive, we call them radioisotopes or radiotopes. And so that's important. And there are different. All atoms have isotopes. Only some have radioactive ones. So it's important that we take some time to go through all that. Now, what we need to do is take a look at some of the implications for this model of the atom and figure out how it explains some of the interesting quirks in the physical and chemical properties of different elements. So what we're going to do is we're going to talk about this concept of electron screening. Now, when it comes to electrons and protons, we need to go to our law of charges. With the law of charges, we need to know that opposites attract, likes repel. Something that's also really important to note, and I'm just going to put it as an aside here because it's going to rear its ugly little head later, is that whenever we're talking about atoms, we're always dealing in 3D space. And so this will have implications on shapes of orbits of electrons and actually shapes of the molecules themselves. But let's take a little look at 3 different elements here. We have lithium, we have potassium, and we have sodium. Now what I've done is, this is sort of a Bohr diagram for each of these. I've done like maybe at a grade 9 level. I've just excluded the number of neutrons not needed for this. What we're going to talk about is just the basics of electron screening. We need to go back to this concept of opposites attract and likes repel. When it comes to a nucleus, the protons don't go anywhere. We have neutrons in there to sort of hold the nucleus together. They're thought of as the glue. As you get heavier elements with more and more protons, you'll notice that you'll see a lot more neutrons in there to sort of space the protons out so that the nucleus doesn't explode from the positive charges trying to flee from each other, repel each other out. But the electrons are thought to be moving in space, and they're found in these set energy levels. We don't call these orbitals at this point. That will be something for a little bit later. So we've got these energy levels, and the electrons sort of exist in here. We've created this mathematical concept of where an electron lives. Now, it's important to understand that these electrons are going to want to stay as far apart from each other as possible. But we also need to understand that the electrons are attracted to the nucleus. And what we're going to do is just take a look at this concept of screening. Whenever we have electrons that fill an energy level, like in the case of lithium, we have 3 electrons. The first 2 are found in the first energy level, and that energy level is full with only 2 electrons in it. That would be helium, the noble gas, the first noble gas. Lithium has 1 extra electron than helium. It's found in the second energy level. Lithium is also found in the 7-second period, or the second row of the periodic table. Now what happens is we have a full energy level here, and it is going to alter the effects that this outer electron or valence electron will feel from the nucleus. So as it turns out, depending on where an electron is, it will feel the pull towards the nucleus differently. So if we look at something like the inner electrons, we'll notice that the inner electrons will feel a strong pull because they're really close. Now when we take a look at the outer electron, because it's further away, it doesn't feel quite the same pull. So we could think of these inner electrons as having twice the amount of pull towards the nucleus because they're closer. Now, this outer electron is shielded or screened from the positive charge in the nucleus by this full energy level. I can think of it maybe as like a moat around a castle or something. Making it more difficult for the electron to feel the pull towards the nucleus. And so we've got this concept of screening taking place. Now as we go down another period or another row in the periodic table, we add another energy level, and it's full. And if we look, we can set up a simple ratio, what I would call screening to proton ratio. So here we have 2 electrons screening 3 protons. Now when it comes to sodium, we have 8 or 10 electrons being screening, and we have a positive charge of 11 in the nucleus. So this is interesting. We go from a 2 to 3 ratio all of a sudden to a 10 to 11 ratio, right? When we break this down, 2 to 3 is sort of close to 50-50, but 10 to 11 much more closer to 50-50. When we look at potassium, we have 18 electrons shielding a positive charge of 19. Again, we're getting closer. We're getting much closer ratios as we go, and what we're finding is that every time we increase the number of full orbits, or full energy levels, sorry, we are increasing the shielding. So if I were to compare the pull of electron A to electron B to electron C, the pull or attraction for A is greater, much greater than B, and B is greater than C. Now this is going to have implications for some different characteristics that we'll find in the periodic table. The four really important characteristics that we need to think about is ionization energy, which is the energy required to remove an electron, electron affinity, which is the energy released from adding an electron to an atom, atomic radius, and electronegativity. In the follow-up lessons, we're going to talk a little bit more about these and look at how this concept of electron screening, which all is derived from the law of charges, how this plays a role in creating patterns that we notice from collecting data of different elements in the periodic table. So the next lesson will be on ionization energy and electron affinity and comparing the different values of elements in the periodic table and trying to decipher why they are the way they are.